Hello everyone, Professor Dustin here, and this video is going to be about how to do linear regression analysis using Google Sheets and do it correctly. So I'm actually going to check what Google Sheets does against a couple of other sources to make sure it's actually telling us the right answer, because it's not at all clear based on what the spreadsheet function says that it actually is doing the right thing. So I'm just going to check in this video. Now, I can't just check. I just can't help myself but give you a little bit of theory about what's actually going on behind the scenes. So first I'm going to jump into that. I'm not going to go completely through the calculation. I'll just show you in essence how you can get how linear regression works, how you find the very best fit using statistics, and how you get the how you actually do the calculation using some calculus. So let me discuss a little bit about that, and then we'll get into actually how to do the spreadsheet stuff. You can just jump to the end of the video if you don't care about the theory, you just want to see the spreadsheet thing. So for just a little theoretical background on how this error calculation works, we're going to look at the Gaussian distribution. So the Gaussian distribution, you might know, is the distribution of measurements if something is really randomly determined or not correlated with anything else. So you can think of it like if you are going to throw a penny and you throw it the same way every time, that penny is very likely going to end up in the same place, but there's going to be a certain spread. And if there's no correlations with how you throw it, like maybe the temperature doesn't change so it gets colder, there's no wind, everything stays exactly the same, most of the pennies will fall in the exact same spot, say some distance away from you. But some of the pennies will deflect and land in slightly different places at distances that are specified by the value sigma. That's actually the standard error. This distribution is called the Gaussian distribution. In fact, I guess I might as well mention the way that sigma is defined, so that there's a certain number of measurements that fall inside plus sigma and minus sigma. And the total number of measurements that fall inside there is 68.28% or something. But if you repeat the measurement over and over and over, you throw your pennies over and over and over, 68.3% of the time you will get between minus sigma and plus sigma of your average. That's actually how you define the standard error sigma. Okay, so how does this help us with our linear regression analysis? First of all, you assume that the variables are going to be defined via a Gaussian distribution, meaning when you make your measurement, you're making a measurement on a random error. The error is not correlated with anything else. Now, there's an equation that governs this curve for the Gaussian distribution. And the equation is this. It's normalized with respect to the error right there, and actually the error appears in the exponent as well. But the equation is basically x minus x bar, so x bar is the best value in the center, x is each particular value down here, and divide by the error. So this tells you the probability distribution here. And notice this is a relative probability, so the total number of stuff in here is 100%. That's how it's normalized. But it is relative, so that, here and here have 50% different probabilities, but we don't actually know what the probability here is. You'd have to go and calculate that. Okay, well, how is this going to help us figure out what the line of best fit is for our instrumental data? Well, so remember, our particular experiment we're talking about in free fall, we have a plot of time versus velocity, and we want to figure out what the line of best fit is going to be right there. And that's going to be an equation, which is the velocity as a function of time, which is v naught plus g times t, where g is the slope and v naught is the v-intercept. So we want to cast this into a form which we can use this for. So we have to be a little careful with the variables. The thing we're measuring here is v, just like the thing we're measuring here is x. So we have to be a little bit careful when we're casting this formula into this. The x up here is actually the measurement variable, so this is going to be v. And actually, we have a whole bunch of different v's. So it's going to be like vi, where we have like v1, v2, v3. The best value up here is actually going to be our model fit. So it's going to be the best fit for the line. So that is actually going to go into the x bar. So we're going to replace, we're going to do this exponential for each point. And each point is going to have a vi, and it's going to have a best value. The best value is going to be given by our formula here. So let me rewrite that. So that's that. And notice what I've done is I've labeled the uncertainty with v, because that is actually the uncertainty we're talking about, the uncertainty on the result of the measurement. I've replaced the best value with our fit, because that's what we want, the best value. We want the best value to follow that line. And then I've noted that this is the probability of just one v, not all of the v's, just one particular measurement. Now, of course, we want the probability for the entire set of our numbers to be what it is. We want to know what the probability is that we took every single data point the exact way that we took it. So if you remember probabilities, if I flip a bunch of coins, you take the product of the probabilities of each coin to determine like what the probability is that I get like all heads or something, right? So I want to do the same thing here. The total probability is going to be the product of all of the probabilities for each individual one. Well, so if I take that and I take my equation up here and I plug it in there, each of these probabilities means that there's a product of exponentials. And then if you take the product of a bunch of exponentials, that means that you get the sum of the terms of the power of the exponential in the exponential. So the result of that is going to be the following. So notice I get n factors of that uncertainty, right? So I get n factors of those because there's one for each one in each probability. And I get the exponential of a big sum of each one of the terms up here, which looks like that. So a sum of n values. So I should probably write this as I from 1 to n. This thing that I wrote up here takes a very special name. This thing is called chi squared. So chi being the Greek letter chi squared. That's actually a parameter to discuss how good your fit is telling the community what your chi squared is. You'll often say, oh, my chi squared was this or this, and that's a relative measurement of how good your fit was. But for our purposes, what we want to know is how to actually determine what the best values for that V naught and that G actually are. And to do that, you simply use a bit of calculus. So if you want your probability to be as high as possible, meaning that the line that you use is the highest probability line that corresponds to your data. You want to make sure this thing is as big as possible. Well, so this is an exponential of a negative number. So making this thing as small as possible means you're going to make this thing as large as possible. And if you recall, how you do that from calculus is you just take derivatives. So if I want to find the best value of V, I take the derivative of chi squared with respect to V naught, let's say. Derivative of V naught, set that to be 0, and then you can solve for V naught. And if you want to find the best value of the slope, take the derivative of that with respect to G, set that to be 0, and then solve for G. Now, of course, the process by which you have to do that is a little bit complicated. It requires some calculus, and then you get like a set of equations because this is a sum. So then you have to invert the set of equations, and so it gets a little theoretical basis behind it is just an applied calculus problem. So let's say you do that. You find the best value for V naught, and you find the best value for G. But of course, like the thing we really want to get at here is we want to find G plus or minus the sigma on G, and we want to find V naught plus or minus the sigma on V naught. Now, in our particular lab we're doing this week, we don't really care about V naught. What we care about is G, but in principle, we can still find the uncertainty on that thing. Okay, so how do we do that? Well, now we go back to the propagation of errors formula that we studied in the lab last week. Although I'm not showing it because it's complicated, we now have a formula for V naught and a formula for G. So if we know what the errors on V naught and the, not the errors on V naught, the errors on our measurements, VI, and our measurement T, then we can use the propagation of errors formula to find the errors on this value and the errors on this value. Remember, it's the square root of some derivative squared summed up. It's kind of a nasty formula, but it is like closed form. You can write it down. But once we get to here, if we're just going to be doing this all the time, it's much easier to just look for a spreadsheet function that actually does it. So I'm going to go on to showing you what the spreadsheet function is in Google Sheets that is actually going to tell you what values like this are and also what the errors like this are going to be. Okay, so now looking at the actual data we have, I'm doing this for the free fall lab, but of course this will work for any kind of linear regression you have. I generated some fake data. Of course, I generated it using the real constant due to gravity, 9.81, and then I added a little bit of scatter to make the data actually scattered. So here's my time, here's the velocity. Of course, the data you gather might be the position, then you have to take the finite difference to get the actual linear slope. I'm not doing this for a polynomial like a t squared plus t thing that you would have to do for the position. That would be a totally totally different calculation. As far as I know, Sheets doesn't do that. It's not impossibly hard to do that, but it would just require a little bit of work, right? So this is just going to be linear regression, not using any higher order polynomials. So time, velocity, here's a plot, and you can see that I fit the best fit line. This is just the Google trend line thing. So the first thing to do is to check to make sure that that Google is kind of self-consistent when it comes to what is the best fit line. You can pull the slope and the intercept out of the plot, I mean, without using the plot at all, by using the spreadsheet function slope, and then you just have your notice that the values are actually flipped for everything Google does relative to what I would think would be the default. I would think that you would put time velocity as like X, Y, but actually it's flipped around. So you put the Y in first, in this case, the velocity, and then the X, which is the time. That tells you the slope, that tells you the intercept. Those both fit on the plot, so I'm going to assume those are actually the correct values. So what I did is I went over to Wolfram and I Googled the least squares method. I'll put a link in here to this website, and I got the whole description as well as a formula down at the bottom for the standard errors. Now, this didn't look that familiar to me. What I'm most familiar with is this book by Taylor, this book, which has some amazing stuff in it for how to do linear regression. I don't really understand the Wolfram. I understand Taylor. I understand this book very, very well, and that's what the theory that I just gave you was from. So I decided they really should check both because the formulas look quite different. Actually, if you look up in Taylor, this is not the standard error formulas. They are simpler. So anyway, so I tried both. So here's me doing the error calculation using that page I just showed you. And here's me doing the error calculation from Taylor. This is the error on the slope. This is the error on the intercept. S and R are just for doing some checking and stuff. And you can see that the slope error and the intercept error match exactly the same. They're flipped around. So obviously I flipped them. Sorry, that one is the error on the intercept and that one is the error on the slope. Okay, but you get where I'm saying. I just flipped the nomenclature. Okay, so the first thing I did was like, okay, I can now verify that I believe that Taylor, which is the reference I believe in, matches the Wolfram reference. Good, we know how to calculate errors. And I had to use all these extra columns in here. You can see it became super nasty to get it, whatever. So what can Google do? So here's me plugging in some things from Google. Standard error YX, CoVar, Corel, R squared, all that stuff. Okay, so the R squared is something. It's called the R, it determines how good the fit is. And that standard error XY is also something. So you can see that it's S in the Wolfram approach. It's actually the standard error on our calculation of velocity. So if you want to know what the error is on each measurement of our velocity, it is actually this. You can type STEYX, make sure you flip the X and Y's, and you actually get the right answer right there. So cool, that's the error on our measurement. But actually, we don't really care about that. What we mostly want to do is the slope error and the intercept error. Nothing that I sort of Googled my first time out told me the actual correct answers for the slope and the intercept. You have to go one step further and look a little closer. You need to use the line ST function. So the line ST function accepts as inputs the Y data and the X data. Remember, it's flipped around again. So just like all of these, C comes before B. So you want to put in the Y values before you put in the X values. Kind of annoying, but that's the way it is. And then you put in 1 and 1 for the last two values to line SC. This just tells it to like calculate the intercept or something. And this tells you verbose. So you can see what's right here. What's it telling you? Known data Y, known data X, calculate B. I think that's the intercept. And then tell me everything. So 1 is tell me everything. I think if I set this to 0, it will tell me less things. Yeah, it tells me almost nothing. It actually tells me the slope and the intercept. Okay, fine. But if I really want it to tell me everything, I have to change that to 1, and it gives me this big giant table. And you can see right in there are the two values we care about, 64 and 7. So that is the And so when I went down here, I tried to explain what each of these things is at least tells us the slope and the standard error on the intercept, and the standard error on the slope and the standard error on the intercept. I have no idea what these following values down here. You can see they don't match anything from either Taylor or Wolfram. So they are just some other parameters to tell you something about the fit, but we can basically ignore them. So the end result here is use line ST function in Google Sheets to tell you all the information you need. It tells you the intercept, the slope, the intercept, and the errors on the slope and the errors on the intercept. So based on this, I would report my value of G in my fake data as
1007 plus or minus 64. So 1007 right here, just rounding up, and plus or minus 64. So that's it. So that's how you do linear regression on Google. Again, this is not you doing a polynomial. Polynomial is possible. It just is a little bit more work to do the propagation of errors, as I talked about in the Blackboard part of this video in the theory. So hope this is helpful, and it will let you get to the answer a little bit quicker when you're doing standard error using linear regression. This is really the right way of doing it. Okay, thanks. See you in class.